So, my name is Gilles Lambaré. I am Research Director at CGG in Massy. What I will present you is some recent advances in wave-based tomography, a work and a presentation that was done with several of my colleagues from CGG, Patrice Guillaume and Jean-Philippe Montel. Full waveform inversion is clearly now well established for estimating structurally conform shallow velocity models in area investigated by recorded diving waves. I shouldn't do. Deeper, in area investigated by reflected waves only, velocity model building is still dominated by wave-based tomographic approaches. Let's look at a paper by Martha Woodward and co-authors from 2008. It was said there, over the past 10 years, wave-based post-migration grid tomography has become the standard model building tool for seismic depth imaging. But also, why the basics of the method have remained unchanged since the late 90s, the problem itself has changed dramatically. The method mentioned in this paper was the following. Starting from a velocity model, a pre-stack depth migration where you pick dips and RMO, you perform so first a tomographic retracing and update, a linear update of the velocity model, and you loop, going back to the depth migration, the picking, and so on. This is what we will call later the linear wave-based tomography. In fact, what I want to show here is that since this date, wave-based tomography approaches have known very important improvement and with some real breakthrough. We will go through during this presentation, starting from industrial nonlinear tomography, going to multi-layer tomography, and progresses improvement in constraint tomographic inversion. Finally, looking at the resolution that can be expected from this method, so high-resolution tomography. So here will be the sketch, going through all these aspects. Nonlinear slope tomography. What do we mean by nonlinear tomography? In fact, at the left, you have the sketch for linear wave-based tomography, the one mentioned by Martha Woodward. So you have your initial pre-SDM, you perform your RMO dip and RMO analysis, you update the velocity model and go back to the depth migration. A nonlinear update has the same component, but from the pre-SDM, it's shown on the right, from the pre-SDM you perform a dip and RMO analysis, but there you perform what we call a kinematic demigration. You obtain invariant data. Data that do not depend on the initial velocity model, the one used for the pre-stack depth migration. Then you go in the nonlinear loop with this invariant data, computing some misfit, performing a linear update of the velocity, updating the velocity and doing, again, looping over the invariant data. This kind of workflow provides is in fact much more efficient and flexible. And this results in improved accuracy and faster turnaround. Look at the various types of nonlinear tomographies. Some of them are based on horizon. So, as shown on the left, you perform some picking. You pick event all over the data set. Some other may work with locally coherent event. It's shown on the right. And you have then the potentiality for having a much denser picking, much denser kinematic information. In fact, it is this kind of approach, I believe, can provide the most from wave-based tomography. They are what they call the family of nonlinear slope tomography, which has very old roots among Russian geophysicists in the 50s, but also later at Stanford or at School of Mines of Paris. What is the basis of this approach? Look at this sketch. You have on the left some sketch, some view of the unmigrated domain. At the right, some view in the migrated domain. At the top, common offset panel. On the right, in the unmigrated domain. On the left, in the migrated domain. Look at the migrated domain. You can identify some event in the common offset section. It's localized by its position and its dip. Through a kinematic demigration, you can go back to the unmigrated domain where you will characterize the event, the local event, by its midpoint position, its time, and its slope. And through migration, demigration, you can go from one side to the other. But for the tomography, the important panel are those below. The common image gatherer on the right, the CMP on the left. You can have also the slope, the local derivative of the residual move-out curve in the common image gatherer. And there is a connection through a formula given by Choris and co-authors in 2002 between the derivative, local derivative of the RMO curve and the slope in the CMP gatherer. So you can move from one side to the other. What is on the left is what we call the kinematic invariant, is what is obtained through the kinematic demigration process. What is on the right is what is used for assessing the quality of the velocity model. In fact, in this kind of approach, the aim is to obtain the minimum DRMO over all the picked events. So there are many developments that have been done around nonlinear slope tomography, and you can build a very strong platform based on this. Key components are the use of a gridded velocity with 3D TTI. Another important component is the use of the potential use of the migrated facets, the visualization of the migrated facets that can be used for QC. A very important point, the flexibility, the potentiality to combine, to integrate workflow. You can do everything in depth, on the right, performing the picking in the depth domain and then going through kinematic invariant to an update of the depth velocity model. But you can do it also in time, going from a pre-stacked time-migrated cube, where you perform the picking, to kinematic invariant, allowing you to update in depth or in time. All these result in improved accuracy and turnaround. And also, thanks to the fact that we have a nonlinear approach, an easier way to constrain inversion. Multilayer tomography now. Multilayer tomography comes from the need, in some context, to introduce explicitly sharp velocity contrast in the tomographic velocity model. This is the case for the salt. This is the case for the salt layer in the North Sea. Here I show you an example from a paper by Evans and co-authors. You have on the left an image, depth-migrated image, obtained with a smooth velocity model. A smooth velocity model across the salt layer, which is in the center of the image. On the right, same image, but obtained with a velocity model where you have at the top of the salt layer a strong velocity, you have a strong sharp velocity contrast. Introducing the complexity of the top of salt as a sharp velocity contrast allows you to delineate, to correctly image the structure below the bottom of salt. So there is this need. There is some solution. The classical solution is to perform wave-based post-migration grid tomography by a layer stripping approach, where you first update the first layer, you then perform depth migration, you pick the horizon, the bottom of the layer, you fix it, you introduce a sharp velocity contrast and go to the layer below. So it works, But there are some limitations because, for example, it's prone to accumulate errors and it's very time consuming. So there was a need for some method allowing for a global update of horizons and the velocity grid. There is now a solution. Solution I mentioned here, what we call multi-layer nonlinear slope tomography. What are the components? First, a description of an hybrid model involving horizon and velocity grid. The two components of the model, velocity grid, is obtained by nonlinear slope tomography in a very classical way, while the other component of the velocity model, the horizon, are updated through the nonlinear updating process by zero offset migration. You have on the right, the two components, the two types of data in this approach. On the right, the locally current event, peaked with deep, peak with DRMO. And they are demigrated as done by nonlinear slope tomography. On the right, we have an horizon peak in the initial model and demigrated to zero offset, building some new type of horizon, invariant horizon. So it is the way the process is done in this approach, where you have a nice combination of an hybrid model description and an appropriate nonlinear update of the two components of the velocity model. So there has been numerous published examples of this application, of this method in North Sea essentially. But there is a worldwide usage. Everywhere we get better flexibility, but also an improvement in terms of accuracy, turnaround, and resolution. So rather than the North Sea case study, I would like to emphasize this one, which is an onshore case study in Oman, where you see a major fault system greatly improved in terms of imaging by using this approach for velocity model building and also depth imaging as compared on the left to the pre-stack time-migrated image. Constraint tomography, another aspect which has been greatly improved over the recent years. So, wave-based tomography is an inverse problem, an ill-constrained inverse problem, which requires constraint, or in other words, a priori information. There are numerous types of a priori information. For example, you can add some type of seismic data, diving waves, VSP, surface wave, or non-seismic data, gravity, measurement, and so on. You can also constrain a priori information on the velocity model itself. Smoothness, structure, discontinuity, anisotropy, all that can be introduced. But you can also introduce constraint on the reflector, the dip of the small locally current event you have picked. And this, you can introduce some positioning, some shape, some fitting to the well, some interpretation. A last class of information on the velocity model is any information coming from geological or geomechanical consideration. Finally, you can also introduce information, a priori information on the data, typically through some covariance matrix on the data. So all these, you have seen a lot of work on all these topics, and they have brought over the last 6 years a lot of industrial solutions. So there has been numerous publications. Just to mention some of them over the last 2 years, you have the list just below. What would I like to emphasize among all this work? There was a lack in wave-based tomography of structural continuity. You have there some solution through, for example, steering filter, some way of improving the structural conformity of a velocity model in wave-based tomography. This is a publication by Olga Straveva showing the benefit of using some steering filter and explicit constraint to obtain some velocity model with some structural conformity. Another interesting approach. Sometimes, when performing depth velocity models, the resulting velocity model does exhibit some distorted structure, which are observed on pre-SDM. Here you see one with this pull down, and here is the interpretation. In fact, this pull down is associated to shallow velocity anomaly, which have not been recovered by RMO tomography. So they appear at short offset, they appear differently at bigger offset. But the problem is how to solve it, how to have the information that we like to remove this pull down effect all over the migrated section. So there is a solution published recently last year, deep constraint tomography. What is the idea? To identify location where you have some error in your dip field. You have what you have picked in terms of dip and what you would like to expect in terms of dip. So you can use picking it in a volumetric way on a multi-offset gather. You have a way to constrain jointly with the RMO information the velocity model in your tomographic update. I show you there an example, a comparison for a channel system in North Sea. And you can see in the center the resolution that can be obtained with this approach. It is compared on the left with a manual approach where you pick some horizon and perform some 1D correction. It is compared on the right with full waveform inversion. So you see the resolution that can be obtained with this, in this case, with this kind of approach. High resolution tomography. So there is a very old statement in seismic imaging, which was that typical tomography results can give apparent frequency in the velocity model of up to 2 to 3 Hz. This came, and this was emphasized in the long time ago, for example, by John Claerbout, as a part of the, in fact, of the resolution, potential resolution of seismic imaging from surface data. So you have this very famous sketch by John Claerbout, where you see the resolution in terms of vertical frequency obtained with velocity analysis, and the resolution that can be obtained from the amplitude of seismic trace within the reflectivity bandwidth. And you see between the both, between 2 and 10 Hz, there is a gap. And for long there has been this gap. What is curious is that when we looked at the RMO information in a dense way, the RMO information is what is used for the tomographic update. We observe structure. We observe structure which typically have resolution within this gap. So far, it appears that nothing was really published to show that it was possible to use this information to update the velocity model within the gap, the mid-frequency gap. I will show several examples, several publications that show that it is possible. First, this one by Martha Woodward, the same as the beginning. Performing a very dense picking in position, dense in position, dense in lateral position and in vertical position, without applying any steering filter. In this paper, it shows that you can resolve wavelengths of 400 meters laterally and 300 meters in Z, with a very nice delineation and structural conformity. Other publication, this one by Fruehn and co-authors, using gridded high-resolution tomography, dense peak again, up to 20 meter vertical spacing. And you see there is some possibility with tomography to resolve a very thin layer, a 50 meter thick layer. Here another example published last year at EAGE by PRD, showing a new high-resolution tomography based on an accurate dense volumetric peaking and a differential criterion. What is interesting is that the vertical resolution he obtained is up to 6 Hz. Finally, let's mention high-definition tomography. Another approach, similar aim, resolving for all the detail, going to tomography, high-detail tomographic result. And have a look at the famous Claerbout sketch through these examples there. Here you have the bandwidth, the frequency, and the amplitude associated with the reflectivity part, the pre-STM image. Here what is obtained within the velocity model, obtained with high-definition tomography, converted to reflectivity, with some simple hypotheses on the density, and here is the resulting spectrum obtained. You see, there are between the two curves very limited gap. The mid-frequency gap is by a part filled by the new type of tomography. Finally, with this vertical resolution up to 6 Hz, we have also the possibility, the opportunity, through the new type of broadband acquisition, to be in a situation where there is an overlapping of the resolution obtained from the reflectivity and the one obtained from the tomographic approaches. So, by the end, we see that there have been very significant improvements over the recent years, even on the theoretical basis. And these improvements have largely increased the stability, efficiency, and resolution of wave-based tomography. All over, we have now an increased resolution, a filling of the mid-frequency gap, and we can say up to 6 Hz. But we have also, thanks to the development of new type of acquisition with providing broadband data, we have now a clear overlapping of the both resolution. I like very much this assertion by Dave Nichols 2 years ago. We can say that we have moved from having a spectral illumination gap to having multiple information sources that have overlapping wave number content. The optimum combination of all sources of information remains a challenge. And this one by Pierre Hardy last year, tomography has not been fully exploited. It's clear that structural complexity, stratigraphic data, shallow heterogeneity, poor pressure prediction, all are affordable more than we can expect by tomographic approach. Finally, I believe it will provide some key for understanding and improving full waveform inversion and wave equation migration velocity analysis. So I would like to thank Pierre Hardy and Jan Jones for very fruitful discussion about the topic, and thank EAGE for the authorization to present this result. I would like to say also that this presentation was also given during EAGE annual meeting in 2014. Thank you.